Hello, today we're going to look at sequences and series, both arithmetic and geometric sequences and series, and what they mean and how we can solve the problems you'll be presented with. So the first thing I want you to do is look at this and pretend like all these lines are made of toothpicks. In the classroom, I'd have the toothpicks laid out for you so you could try this out yourself, but you can gather some toothpicks and do it if you want, or you can just draw lines on the worksheet I've got provided for you in the resources. So it says the figures below are made with toothpicks. The first one is made a triangle like this. The second one is completed like this. Notice how many more toothpicks it takes to complete the second shape versus the first. And then we have to add some toothpicks to make the third and even more to make the fourth there. So it wants to know how many toothpicks it would take to make the fifth figure. So if we continue this pattern on. So I want you to pause the video, look at the pattern, and figure out how many it would take to make the fifth, and then how many it would take to make the sixth one. So one of the things I like to do is just say, okay, this is my first term, so I'm going to call this a sub 1. This is my second, my third, and my fourth. I know we've got it written right here, first, second, third, fourth, but writing it as a subscript like this is going to set me up to learn how to write these in the future when it's not so concrete of an example, but more just like numbers. So a sub 1 just means my first term, a sub 2 is the second, third, fourth, fifth, and sixth. And then below that I'm going to write how many toothpicks is in each one. So my first one has 3 toothpicks. My next one has 5. And then we have 7. You can count them up: 1, 2, 3, 4, 5, 6, 7. And then 9. And so as I look at this, hopefully you see a pattern there. You know, you can say, am I multiplying 3 by something to get 5? No. Neither am I dividing or subtracting. It looks like I'm adding 2. And then I add 2 to get this one, and add 2 to get this one. And so it makes sense that our fifth one would have 11, and our sixth one would have 13. It says, can you figure out a formula to help you find the number of toothpicks for any figure? Make a table to help there. So let's make a table. So here's the table I made. This is the nth term, so this is like our a sub 1, a sub 2, a sub 3, and so forth. And this is the number of toothpicks in it. So it's pretty easy to see that if I put a 7 right here, that this one's going to be 15. But what if I asked you for the 100th term, or a sub 100? You don't want to keep adding 2 and adding 2 until you get there. You want to see a pattern and come up with a formula for it. So we can see that if we were to graph this, look at this as a graph. So just sketching this out real quickly, we have our first, our second, our third, fourth, fifth, so forth. Our first term would be at 3. Our next term would be at 5. Our next term would be at 7, and then 9, and then 11. And notice this is starting to look linear here. And so what does this jump of 2 represent? For every increase on the x-axis, our x-axis here is our nth term, our y-axis is the number of toothpicks. But for every 1 that we go over, we go up 2. Oh, that's the same thing as slope. So this is actually can be written as a linear equation like we did in a previous lesson, where y is the number of toothpicks, and the amount increasing here is our slope, so we have 2x. X is the term you're on, or the nth term. But the problem is I need a y-intercept right here. So I need to figure out what the y-intercept is, and that's when x equals 0. So if I were to take this back, let's put in an extra term right up here. If you were to move it backwards and actually come up with a 0th term, how many toothpicks would it have? Well, going by this pattern, you're decreasing by 2 as you go up. It would have 1 toothpick. So this thing crosses at 1. Now, sometimes that makes sense in a word problem, sometimes it doesn't. It really doesn't here, because how do you have a 0th term in this word problem? But it does allow me to come up with a y-intercept for the rest of the word problem. So our y-intercept here is 1. So y equals 2x plus 1. That's going to be our equation for it. And you can test it out. So what about our 7th term? If I put a 7 in there, I get 2 times 7 plus 1. 2 times 7 is 14, plus 1 is 15, which is what we had. And you can check it with any of these. Now, if you want to know how many would the 100th term have in it, you can put it into this equation here. You can say that y equals 2 times 100 plus 1, or 201 toothpicks. So the 100th term would require that many toothpicks to get it going. All right, let's try out another one. Let's actually not start there. Let me go back. There we go. It says the figures are below are made with matches. Matches, toothpicks, whatever you're going to make them with. How many matches would it take to make the 4th figure? How many to make the 5th? And then come up with a formula. Pause the video and try that out. So our first term here has 5. Our next one, well, you got the original 5 right here, plus 1, 2, 3, 4, so 9. The third one, we're going to add another 1, 2, 3, 4 to it, so you get 13. So if we're making this chart here, we have the first term has 5. Let's make that a 1. The second term has 9, and then the third term has 13. So it's like your slope in this case is 4. But we need that y-intercept. So figure out that 0th term. So if I go back 1, this is going to go back 4. Once again, your y-intercept is 1. It's not always 1, but in this case it is. So y equals 4x plus 1. That's our equation. And I find that sometimes easier to figure out first is your formula or your equation. And then the 4th and 5th figure should match up with that. We can continue on, though. The 4th figure is going to be adding 4 to this, so it should have 17 matches. And then add 4 to this one and you get 21 matches. You can check your formula. You say, well, if y, for the 5th figure, if y equals 4x plus 1, that would be 4 times 5 plus 1, which is 21, and that matches up. Now, without that concrete example, I want to go over a way we can do it without coming up with the y-intercept. So here's just another way we can do this. When you're given a sequence of numbers, all right, sometimes there's a pattern and sometimes there's a not. If the pattern is just adding the same number and over, we call that an arithmetic sequence. So the two that we just did were arithmetic sequences. It's just a list of numbers, and they just so happen to have a pattern of adding the same number over and over. In this case, let's look for the pattern. So 7 minus 3 is 4, so I'm adding 4 there. 11 minus 7 is 4. And so as I look at this, I notice the pattern here is adding 4 again. This time we have a different start number, though. We're starting at 3. But either way, we're adding the same number. That same number in an arithmetic sequence is called the common difference. So here our common difference is 4. Sometimes there's a common difference, sometimes there's not. If there's not a common difference, it's not arithmetic sequence. So this is an arithmetic sequence, and in general we can come up with a formula for our arithmetic sequence like this, and I'll explain how we get that. So this means it's any term in the sequence. So let's go ahead and label our terms here. This is our first term given, then our second, third, and we take it on out to the 7th term in this case, and it keeps going on like forever. But let's pretend like we didn't know the 7th term was 27, and we only knew this. We wanted to know what the 7th term is. There's two ways we can find out. One, if we know the term before it, the 6th term was 23, and we know the common difference, we can just say, take the 6th term, whatever it is, and add 4 to it, and you get the 7th term. But that's not always convenient, because if I asked you for the 100th term, well, you'd need to know the term before it, the 99th term. And to find a 99th term, you'd have to know the 98th term, and so forth. So a lot of times it's easier just to jump to the end there. So let's pretend we didn't know any of this right here. And I just knew the sequence as this, 3, 7, 11. Those are the first 3 terms, and I said find the 7th term. So without knowing the 6th term is 23, how do we do that? We use this formula right here. So what this says is, if you want to know the nth term, in this case n is going to be 7, you take the first term, I know the first term is 3, and add to it n minus 1. Well, what is n minus 1? N is 7 in this case, so 7 minus 1 is 6 times your common difference. So you need to know the common difference, and we figured that out to be 4. And it says that will give you your 7th term. 4 times 6 is 24, and add 3 to it, and you get, let's add 3 to it, you get 27. So the 7th term is 27. Now, that should make sense on why that works. Let's go back and look at how that could work here. Now, remember that multiplication is the simplification of addition. So we're adding 4, we're adding 4, adding 4, and adding 4 right here to get to this 6th term. But also we're adding 4 to get to the 7th term, and from the first term we had to add 4 right here. Now, this formula does not know what the first term is, so it doesn't know it's 3. It's supposed to work every time. Otherwise, we could just put a 3 there if our sequences always started with 3. So how many times did I add 4 starting from the first term? I added it 1, 2, 3, 4, 5, 6 times to get to 27. So I'm adding 4 6 times. So the simplification of addition is multiplication, and I'm multiplying that out. But like I said, this could have started with 23, it could have started with 3, it could have started with 100. In this case, to get the correct number, you got to tell it what is it starting with. It's starting with 3, and so we need to add that in there. So because it has that common difference, we can simplify it and say it's 1, 2, 3, 4, 5, 6 times. We add the 4, and then you add the first number. That gives you the total. So that's why the formula works. On all of this, you don't really need to know why the formula works, or even the formula. I'm going to give you that on quizzes and tests, but I think if you look through and try to understand it, it makes sense to you, and it keeps you from making mistakes, and you gain some knowledge there. It's good at working your brain. All right, try this one out. Determine if it's arithmetic, and if it is, tell me what the next 2 terms are. All right, so is it arithmetic? The way to do that is just to compare the numbers in between. To go from here to here, what do I have to add? 8. Do I add 8 to get to there? Yeah, and check them all. And yeah, the common difference is 8. This is our first term, our second, third, fourth, fifth, sixth, seventh. I want to know the 8th term and the 9th term here. So there's a couple ways you can do this. The easiest way is to say just add 8 to it, and you get 51. Add another 8, you get 59. Now, give me the formula for any term I want. So to do the formula for any term, this is what you're going to do. You're going to say, okay, for any term, a sub n, plug in the numbers that you know here. We know the first term, it's -5. We don't know what term somebody's going to ask me, so I just leave it like n minus 1, like that. And I know the common difference is 8. That's an acceptable way to do it. If you were doing it in the y equals mx plus b format like we did on the first example, you can do that as well, but you need to know what the 0th term is. So to figure out the 0th term, you need to go back 8, which puts us at -13. And so our slope is 8, and our y-intercept is 13. That should work as well. In fact, we can make this look like this. Just distribute your 8, and then combine your like terms. So -5 and -8 become -13. And notice the only difference is what variables we chose. Instead of saying y, we say a sub n. Instead of saying n, we say x right there. I'll take either format as a correct answer. Now, if you can get that far, you should be able to tell me something like, what is the 100th term? So the 100th term, or the a sub 100, if we continue this on without figuring out the 99th term, we can just put 100 in for x and then calculate it out. So 800 minus 13 is going to be 787. So the 100th term is 787 if we continue that on. Now that we have that knowledge, let's take a look back at the worksheet here, and now we're playing with square tiles. We have the 1st through the 4th term here. We want to know what the 5th figure will be, what the 10th figure will be, and a formula for it. So pause the video and try those out. So for the first term, a sub 1, we have 3, 6, 8 tiles to it. For the next one, a sub 2, we have 4, 8, 12 tiles. For the third term, we call it a sub 3, we have 5, 10, 16. And based on this, it looks like we're adding 4 again. Let's just see if this one has 20. This is 2, 4, so that's 6, 12, and then plus 8 gives me 20. So yeah, we are adding 4 each time. So our common difference is 4. So if I'm writing out the equation, I know that we've got 4x. And what would the 0th term be right here? Our 0th term would be a 4. We're going to subtract 4 and get that, so my y-intercept is 4. So there's our formula. And then I want to know what the 5th figure is going to be. It should be 24, just adding 4 to the previous term. But what's the 10th figure going to be? Well, put 10 in for x, and you get 4 times 10 plus 4. And so you get 44 is your 10th figure. So this answer is 44. This one's 24. And then our equation is right there. All right, now we're going to turn our attention from just figuring out numbers in the sequence to figuring out the sum of the sequence. And when we figure out the sum of a sequence, we call that a series. So in this case, the first thing I want to know is this sequence I've got listed out right here, is it arithmetic? If so, tell me what the common difference is. So here you should be able to see we're just adding 1 each time. So yes, the sequence would be arithmetic. And because there's plus symbols in between them, we're going to be calling that an arithmetic series. So I want to add up the numbers 1 through 100. Now, I don't want you to actually get out a calculator and do that. That's what I normally make my students do in class. That's like their warm-up. And I don't even let them get through it all because it takes a while to add up the numbers 1 through 100. And the legend says that this was given by an elementary school teacher to like her 2nd or 3rd grade class, just as busy work. And within a few seconds, one of the students came up with the answer, the correct answer. And it kind of shocked her, but he was kind of a genius in himself because it was Frederick Gauss. He became one of the best mathematicians out there, one of the last mathematicians to be considered an expert in every field of math. Now math is so broad that you can't study all of math in your lifetime. But anyway, this is the pattern he noticed. Instead of adding it up the normal way, like 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, and so forth, he said, what if, writing out my numbers, I wrote it out like this? I take this 1 and I write it right here. Take this 2 and add it right here. The 3 and then the 4. And I add these like this. Well, I get 101, 101, 101, 101. And if you made it like the next set, 96 and 5, well, 96 plus 5, well, that's 101 also. So he noticed that you're adding up pairs of numbers to give you 101. So the question is, how many pairs would he get? Well, it would be half as many numbers as he has here. So being 100 numbers, he's going to get 50 pairs. So if he took 50 and times, 50 pairs that add up to 101 and multiplied it, you get 5,050. And that's the sum of the numbers 1 through 100. In general, if you're starting numbers 1, we can summarize this to n times n plus 1 over 2. Just to discuss this a little bit, all it's saying is you take whatever your last number is, we're adding up to 100 here, and you're going to say 100 plus that starting number 1. So this is basically what your pairs are adding up to. And then how did we get the number of pairs right here, 50? Well, you took the number you had, once again, n, and you divided it by 2. So you had 50 pairs that added up to 101. That's what this is saying. If we were adding up the numbers, let's see, like this, 1 through 12, how would we do that? Well, we've got 1 plus 12, which is 13, 2 plus 11, which is 13, 3 plus 10, which is 13. So you're just going to say that this is our nth term here. Remember, it's n plus 1 times the number of pairs, n over 2. So n plus 1 is 13. 12 divided by 2 is 6. You're going to have 6 pairs that add up to 13, so the sum is going to be 78. Now, there are a few things that happen here that kind of mess us up. One is we don't always start off with the number 1, and secondly, the common difference is not always equal to 1. So let's take a look at a series where it's not like that. So this one starts off at -5, and we're adding up fewer numbers here, but the common difference is not 1. So first make sure there is a common difference, and that's arithmetic before you try any of this. Let's see, we are adding 3 right here, then add 3, add 3, add 3, add 3. So that looks good. The common difference is the same. But the same trick kind of applies. Take the first term and add it to the last term. What do you get? You get -5 plus 10 is +5. Take this one and add it to this one. -2 plus 7 is +5. This one and this one add up to +5. So you got 3 5s, or 3 pairs that add up to 5. You're going to get 15 as your answer. But how can we make it? Sometimes there'll be more than numbers than this, and we want an easier way to think about it. Basically, if you know it's an arithmetic series, you can say, take the first term and the last term and add them up. So the first term plus the last term and add them up. And then however many terms you have, divide it by 2. So this is a more general formula from the other one that started with 1. This one can start with any number. So how do I apply this red formula here to this situation? I know my first term is -5. I know my last term is 10. And then the number of terms here is 1, 2, 3, 4, 5, 6 terms. So you got 6 over 2. This simplifies to 3 times 5, which is 15. All right, try this series out. Make sure it's arithmetic, and you can pause the video and figure out what your sum is before seeing the solution. So looking at this first, make sure it's arithmetic. I know a lot of these examples, they are, because I'm teaching it to you right now, but we will have some that won't be, and you'll have to say not possible or add it up a different way. So this one, notice each time we are adding 10 each time. So it is arithmetic. So I can solve it using this way. We say 7 plus 97. That's our first term plus our last term. And then how many terms do we have? We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 terms. 7 plus 97 is going to be 104. And 104 times 10 is going to be 1,040. So that there is our sum. Before we get to geometric sequences, I want to show you one thing that might happen. These have all been nice, pretty whole numbers, but sometimes, let's add another example in here. Sometimes it's not so pretty. Let's say we had our starting term was 4, and then we went to 9, 14, 19, and then 24. So in this case, we've got 5 numbers. So notice if I start moving numbers around to add them, like if I move the 4 right here, the 9 right here, this adds up to 28, this adds up to 28, but this one doesn't have a buddy to go with. The 9 and the 4 got moved over here, but notice that it's 1/2 of 28. So you're adding up 2.5 pairs of 28. So it would still work out formula-wise for us if we're adding these numbers up. Let's put some plus signs in there. So if we're adding these up, all you got to do is say take the first term plus the last term, 4 plus 24. And there are 1, 2, 3, 4, 5 divided by 2, or 2.5 pairs that add up to 28. So then you end up with 28 times 5 halves, which is the same thing as 5 times 14, which is 70. So these numbers should still add up to 70. All right, now to talk about geometric sequences. Before we were just talking about arithmetic, that's with a common difference. You're adding the same number. Geometric's a little bit different. Take a look at these numbers and see if you can tell what a geometric sequence is. So you should be looking for a pattern here. If you start off with thinking maybe it's arithmetic, you say, okay, I'm going to add 4. But if I add 4 to this, I don't get 18. I get 10. So it's not arithmetic. We can't follow the rules for arithmetic sequences in series. So in this case, what is the pattern? And it's going to be a multiplication. So I'm timesing by 3, timesing by 3, and so forth. And so this is what a geometric sequence is. It's when you have that same number you're multiplying by. Now that's not a difference, so we don't call it a common difference. You could say that these two have a common ratio. So we use the letter R to mean common ratio, and in this case the common ratio is 3. So this is, once again, a sub 1, 2, 3, 4, and 5. What would be the sixth term? Well, the easy way to do that is just to multiply the previous term by 3. So 3 times 162, doing this in my head and kind of on paper, it's 300 plus 180 plus 6. We get 486. That's the sixth term. But what if I asked for the 10th term? I don't want to keep multiplying by 3 until I get to the 10th term. So just like with arithmetic series, we can, in sequences, we can also have an equation to help us out here. Now, it's not as easy to derive like we had on the last one, but let's take a look at it. That's the one I just showed you to figure out the sixth term, and then to find out any term, it looks like this right here. So this is saying, if I want to know the nth term, take the first term and multiply it by the r to the n minus 1. So I just said the 10th term. How do we figure out the 10th term? Well, the 10th term equals the first term, 2, times our common ratio raised to the 10 minus 1. So 3 to the 9th times 2 would equal our 10th term. So 3 to the 9th is 19,683. I used a calculator. I didn't have that one memorized or completed in my head. And then we're going to multiply that by 2, and we're going to get 39,366 as our 10th term. Now, let's understand why the formula works. Let's pretend like we did not know the 5th term here. So we want to know what the 5th term is, and let's pretend like we didn't know this formula where we can just say the previous one times that. Let's just look at the pattern that's going on. I'm taking the first term and I'm timesing it by 3, and then by 3 again, and then by 3 again, and then by 3 again, and then that gives me my 5th term. So I could jump the second term by multiplying it by 9. So 2 times 9 is 18. I could jump both the second and the third term by multiplying the first term by 27. And then I could jump them all by multiplying by 3 raised to the power 4 here. So watch what's going on. 3 times 3 is the same thing as 3 squared. So 2 times 3 squared would give me 18. Or I could say 3 times 3 times 3 is the same thing as 3 to the third. So 2 times 3 to the third would give me my 4th term. Or lastly here, notice I'm multiplying it 4 times, or 3 to the 4th times this 2 would give me my 5th term. And so in essence what I'm doing is whatever the first term is, that's a sub 1, oops, not a to the first, but a sub 1, times whatever my common ratio, in this case it's 3, gives me raised to the power of n minus 1. Notice the 5 right here, minus 1 gives me the 4 for the exponent. So if you want to know the 5th term, you're multiplying it by that common ratio n minus 1 times, or 4 times there, 3 to the 4th. And so that's how we come up with this formula. It's the first term times r to however many times you're multiplying by r there, which would be n minus 1. Once again, you don't have to have it memorized. You don't even need to really explain why the formula works. I just think it's great for the students that can understand it to give it a try, because it will make you a better math student. I'll give you the formulas in any quiz or test that you're going to take on this stuff. Try out this one. Figure out, is it a geometric series, or I'm sorry, a geometric sequence, and then figure out what the common ratio is. And then let's go with find the, this is 1, 2, 3, 4, 5. Let's find the 8th term. So it is geometric, and we are multiplying this time by a fraction, and the fraction is 1/4. So we times by 1/4 all the way throughout, and so we can say that r is equal to 1/4. A sub 1 equals 65,536. I didn't put commas in here because I didn't want to get confused with the commas separating the numbers. And so to figure out the 8th term, I'm going to use this formula. I'm going to say A sub 8 is equal to the first term, 65,536, times 1/4 raised to the 8 minus 1, or the 7th power. And this is where you're going to punch it in the calculator because it will make life a lot easier for you. And when I punch it in, I go ahead and do this part first, 1/4 raised to the 7th. It's going to give you a scientific number like 6.1 times 10 to the 5th or something like that, or -5. Either way, just punch it in. 1/4 raised to the 7th power, or 0.25 raised to the 7th. Leave that number in your calculator and then just hit times, and it should take that previous answer, this mess, and it all works out to be 4. So the 8th term is equal to 4 there. Now, we discussed geometric sequences. You can also add them up. So in this case, we have 5 plus 10 plus 20 plus 40 plus 80. This one's an easy one that you could probably add up pretty quickly. We can say we got 30 plus 40 is 70, 150, 155 should be the sum of that. But remember, I'm starting off with an easy example. They're not always that easy. So when we're talking about geometric series here, the first thing we want to do is make sure it's geometric, find the common ratio. So 5 times 2 gives me 10. 10 times 2 gives me 20. And so that's our common ratio. R is equal to 2. And this I've already got set up for you. The sum of however many numbers you've got, in this case we have 1, 2, 3, 4, 5. So the sum of the 5 numbers here is equal to the first term. Let's plug that in, 5, times 1 minus the common ratio of 2 raised to the nth power. In this case we have 1, 2, 3, 4, 5 numbers, all over 1 minus r. So let's see what we get when we punch that in. Remember, follow the order of operations. So it says, please excuse my dear Aunt Sally. We're going to go inside the parentheses first and then go to the exponent, 2 to the 5th power. And so 2 to the 5th is 32. So I got 1 minus 32 times 5. I'm going to go ahead and subtract 1 minus 2 is -1. 1 minus 32 is and I'm working right to left a little backwards here, but 1 minus 32 gives me -31. 5 times 30 is 150, plus another 5 there is going to give me -155 over -1, and this simplifies to 155. I know that's way more complicated than what I did at the beginning, just adding those up, but it will simplify harder problems down the road. Like this one. So let's try this one out. It says add the following. So pause the video, see what you get when you add those numbers up. So in this case, you say, what do we multiply 1/4 by to get 1/12? It's going to be 1/3. Remember, multiplying, you multiply straight across the top and straight across the bottom. Then we get another 1/3, and then another 1/3. So our common ratio here is 1/3. How many numbers do we have? We got 1, 2, 3, 4 numbers. So I want to add up the first 4 numbers in this sequence. So our first term is 1/4. Our common ratio is 1/3. And we're going to take that to the 4th power. We're putting it all over 1 minus 1/3. So a little messy. Remember, 1 is the same thing as 3/3. So I'm going to change this out to 3/3. And that will make the bottom a little bit easier to look at, because 3/3 minus 1/3 is 2/3. And then 1/3 to the 4th power. Well, remember, we can make that 1 to the 4th, which is 1. And 3 to the 4th is the same thing as 81. And so 1, I'm going to change that to 81 over 81. All good fraction work in here, good fraction practice. And so 81 over 81 minus 1 over 81 gives me 80 over 81. And we're multiplying that by 1/4. and then dividing all that by 2/3. And then 4 times 81 is going to be 324. And 1 times 80 is 80. And all this is going to be over 2/3. And then we're going to keep it, switch to multiplication, and then flip this. And let's see, is this divisible by 3? Could I cancel something out? 3 plus 2 is 5, plus 4 is 9. So it is divisible by 3. So let's divide this by 3 and get 1. Divide this by 3 and we get 108. I know that 2 will go into 80, so divide that by 2, you get 1. Divide this by 2, you get 40. These two are both still divisible by 4, actually. So this divided by 4 gives me 10, and this divided by 4 gives me 27. And that's as far as I can go. So 10 times 1 gives me 10. 27 times 1 gives me 27. And that's our sum. Now, don't get too afraid if you see this and you're thinking like, whoa, it's a lot of fraction work. And that's what one of the things I like about giving students this is some of them fear fractions. And if you can do this, then you kind of get rid of that fear of the fractions. If it's a good, satisfying feeling when you go through all of that and it works out to be a correct answer. You could have also have added 1/4 plus 1/12 plus 136 plus 108 by finding a common denominator. But it's kind of a pain to find a common denominator there. And then if I made it more numbers than just 4, it would be even harder to find a common denominator and even harder to add them. So this equation right here becomes more useful as you get more and more numbers we're adding up. Now I'll try to get it so that they're simpler problems that you try out for homework and for the quizzes and stuff, but I want to throw something at you and show you that our sequence could have fractions in it, and the common ratio can be a fraction as well. That's how you would work that problem out. So that's all I have for you today. We're going to do that for homework. We're going to work on arithmetic and geometric sequences, and then the series as well, adding those up. Feel free, you should have those formulas copied down. Use those in your notes. You'll be allowed to have those on the quiz and the test, final, and all that, those formulas for it. So, use them. Your job, though, I'm not going to tell you this is arithmetic or this is geometric or this is a sequence and this is a series. I'm not going to tell you which formulas to use or what the equation is. That's your job to figure out, and you got to know how to use them. So get some practice in on the homework and ask me questions if you have any. All right. Thanks for watching.